Good morning. In today's video, or session, we're going to resume from yesterday's video where we had set up the story around what Rusty line async is, why it's important, a lot of basics around command line interface, applications, and how to design them to be more interactive and asynchronous, and deep dive into like standard out, standard in, readline, blocking, and a lot of introduction to Tokyo, tasks, tracing, and so on. So in today's session, we're going to actually do the refactor, which we had sort of set up yesterday. So let me walk you through what I have today. So this is the tcp-api-server project, which currently does this. So you say that's the clap information, and this is quite a bit of clap customization because it uses colors. It's very similar to what Cargo itself does. So if you look at the source code here, you'll find all kinds of interesting customizations. There's a whole thing on clap, which I might actually do a separate stream on because it's not trivial to do like color output for clap that is, rich text with well, rich text in the sense that there's ANSI 256 escape sequences that you can generate. But that aside, coming back to our project, so here we have the server, and let's run that. So the server is interesting because the server's already running somewhere. I think it's running here, so let's kill that. Oh, it's not done. Oh, that's a log. Oops. Where's the server? I have so many of these going. Oh, I see where the server is. It's here. Let me just go ahead and kill this. We don't need this anymore. Okay. So what we could do is run the server here. There we go. So the server's running here. Let me actually kill that and start that again. So here we have the TCP-API server running. And here we can run the client. So if you saw, there was like a nice little animation with the progress bar. And then once that finishes, it shows connected to server. And then what happens is that there's a whole bunch of log messages that are being printed concurrently because there's a bunch of Tokyo tasks that were spawned. And finally, we have, let's see, this message. It goes enter a message, and essentially these are commands. This is the repo loop. And I have to do a bit of cleanup. We can put a little prompt in here because that's a bit misleading. It would be nice if there's a prompt here. So essentially here, there's a prompt there. Oops. Oh, so, right. Oh, okay, there's some flushing issue there. Okay, so when you do exit, that needs to be fixed. This behavior doesn't really work right now. Okay, so there's quite a bit of work to do. And this one, the server seems to be working. So that's good. Let us exit out of this. Okay, so let's go to the main file and walk you through what's going on now. So there's really two code paths. One is spawning the client, the TCP API, the client to really test the TCP API server. It doesn't make a whole lot of sense to have a client application interface embedded in a server unless you want to be able to somehow test the server or configure the server or do something interactive with the server. So really there's two modes. There's the interactive mode, which I'm calling client, and there's the non-interactive mode, which I'm calling server. You can think of it that way from an interaction perspective. So in the non-interactive mode, we don't really need the ability to do Rusty line async because there is no user input. It's just the server does what it does, and there isn't really much more to it than that. It's just functioning sort of as a uninteractive headless thing that's running in your cloud environment. So the client, on the other hand, is if you wanted to interact with a process. That's what you would do the client for. So here, this particular process has dual personalities. It has the server personality, which is a persona, whatever you want to call it, which is uninteractive, and it has a client personality or persona, which is interactive. So depending on which path we take, we're going to either use readline async or we're not. So I'm going to show you the simple path where we're not going to use readline async. Because we don't, there's no user input. When we go down the path, when you say server, oops, it's in here. Actually, let me kill that again. So when you run the server, it's not asking for any input. It's not waiting for you to type something. It's just running. It's just listening for connections. More importantly for the server would be how to configure logging. So for example, here you can see there's a whole host of information around like configure tracing. So you can say, this is more relevant to the server use case. You can say configure tracing, and you can say, you know what, I don't want any logging, or I just want logs being output to a file, which is pretty cool. It actually works. It's been working the whole time. I can show you this in this other screen. So as you can see, this is just I've been tailing the output of, oops, what is this? Why is this being so? Okay, let's start this again. So actually, let's see, tail. I've been tailing. There's actually two log files. If you look here, there's a tcp-api-server and a tcp-api client. Because the way I have tracing set up, and I'll walk through this, is that you have the option of tracing none to standard out to file, or both standard out and file. And also, there's a little bit of more of a little sort of twist at the end, which is that if you pick standard out, whether it's standard out or standard out and file, there's a difference between if it's running interactively or uninteractively. And I'll explain the difference when I talk about the differences between the server and the client. So let's just do this. And now you can see there's like all the previous logs. So basically when I run the server, whatever you're seeing in this terminal is also being dumped in the service. Actually, let me clean up those two files because there's just a lot of, what the heck? Oh, here we go. So let's just delete them, and then let's run the server, and then actually let's run the client as well. There you go. And then when we do, now you'll see, look, there's a client output, there's the server output, and essentially this is like a whole bunch of logging, which is being dumped from both of these. So okay, so that's to kind of show you that how the logging has been working the whole time. So now when we go down the code path of the server, there is really no interaction, and that's what this is, and I'll go into this later. It's all kind of connected. So here, when we start the server, this is really the main. If you look at the main function, it's got Tokyo main, this macro, which basically turns it into an async main function, and then what it does is that it just sets up tracing, which we'll go into later because this actually needs to be refactored out of this crate into this other one, the readline or readline async, and we're going to rename readline async to something else, probably async terminal, rebel async terminal, because it has a lot more than just the async readline in it. It also has you'll see we're going to be taking tracing and the progress bar and a whole host of other things. We're basically going to move this terminal async module over into this crate, and then we're going to rename this crate. So that's in the videos we're going to be going through this journey. And okay, so now let's look at the server code path, if you will, or the subcommand, and it sets up tracing. That's all of this stuff, and then it starts the server. So keep in mind this is still happening on the the main function just called this function. And so nothing interesting here. So what it does here is that it sets up like a control C handler. So this is so that when you do control C on the server, when you're running the server code path or the server command subcommand, you can hit control C and exit, which is cool. This just uses a crate, and it just does a process exit, like nothing going on here. We can make this better later, but for now this is good enough. It sets up a broadcast channel because this server actually is a WebSocket server, and we'll get into like what exactly the server does later. That's not exactly what we're doing right now. We're just kind of like dealing with the interactive parts of the of this command line interface application, this CLI app. So this info macro is for tracing. So whenever you say info or debug or error, it essentially calls into Tokyo tracing, and that's what generates these log messages. And that's just a log level. So there's warn, info, error, and a whole host of others. So let's see. Okay, so this is the main event loop for the server. Once it hits this, it's just gonna be in this loop until you control C out of the server. It's just gonna sit there forever until you control C. So so here, roughly what happens is that the server just it's asynchronous, so it's not blocking. So it ends up waiting for connections on the TCP listener, because it gets the information for the TCP listener from the command line argument. See this address, port, and the defaults are just localhost 3000. But you can specify your own, and then it'll be passed through here. Then there's a whole lot of these calls into diagnostic. This is miet error handling, and there's going to be I'm going to do a separate stream on that, and also a tutorial on developer life, because that deserves its own, just like tracing, it deserves its own deep dive. So here in the main event loop, what happens is this is normally, if you don't use Tokyo, this is a blocking call. But here, I mean, it is in a sense blocking, but it's not blocking in the same way as synchronous code is blocking. So it's not like your thread is going to be blocked. It's more like the task will be suspended, and when a connection is available, it'll be resumed. So if you think about like Kotlin core routines, it's exactly how that works. So so essentially, even though it's quote unquote blocking, it's not really. And I have a whole let's see, where the heck is this? Let me find this. I have this whole thing on developer life where you can see where this one right there. Too big. So if you get a chance to read this, and you can see all kinds of information about what exactly is going on here. This is a really good read. So this is all about like what is going on with the air in quotes blocking. So I'm gonna leave this open here. Go back to this. Okay. So it's not really blocking. It's whatever. Okay. So here we have let's see. So once it gets the connection, that means there's a client which is trying to connect to the server. It gets a TCP stream after accepting the connection, and then it hands off that TCP stream to a new green thread or new task. And then it goes back to waiting for incoming connections. So not that interesting. And this is the main. So this task that's executing the main loop. This is really the business logic of the server. And this is not interactive because it's not waiting for the user to type anything. The Control-C handler has already been set up. So here we do not use Rusty line async, and we do not use Rusty line async's standard out because there's no need to. We just use normal standard out, standard error, and there is no use of standard in. And so this is very simple. I just wanted to show this because not everything needs to use Rusty line async or that async terminal, because this has nothing to do. There's no interaction here at all. So here it just essentially waits for data to come in from the client, or there's a broadcast channel for the WebSocket behavior. So essentially, if one particular server, let's say there's like 10 clients connected to the server, there's a special kind of message what a client can send to the server, and that will result in that server broadcasting that message to all the clients. So we'll implement that behavior later. There's a whole protocol for that, which I haven't even touched upon, but again, that's for a separate stream. So that essentially is a server. There's a whole lot. I mean, it's very simple relative to the client, if you want to think of it that way. And also, there's no dependency on terminal async, so we're going to remove that. Okay, so now let's go to the main function again. Here you can see, so that was the server, so let's put that to the top. Simple, the simple one. Let's put the client one on the bottom. Okay, so now this is non-interactive. No need for terminal async. And this is Dr. This is interactive and needs terminal async. Okay. Actually, since this is okay. It's just a work in progress. I'm just like saving all this to the Git. Okay, so let's go look at the client, because this is where the now we're going to start refactoring, because as soon as we touch the client, all of a sudden we have this thing where there's this terminal async thing that needs to be built. There was a bunch of bugs we found that needs to be fixed, and so it's kind of like the journey begins to refactor. So the first thing to consider with this terminal async is that it really behaves as a wrapper on top of this async readline. So it's almost like an integration layer. And thus it doesn't really belong in this TCP-API-server. This is really just some glue that an application that uses this crate would need to write every single time, and so might as well put this in the crate itself, so it just makes it more accessible. So that's one thing we're going to do, is just take this terminal async out of this whole module, actually, out of this TCP API server repo or crate, and move into the what we're calling Rusty line async, which will probably soon be renamed to Rebel terminal async, or Rebel async terminal. I'm not really sure. Naming is hard. So let's see. So what this readline, let's see. Let's look at the example. Actually, no. Let's look at the implementation of readline. So this is the async readline. It's meant to be a replacement for the sync readline, and it's just a struct. And the way you use it is that you have to create a new struct, and you have to give it a prompt. That prompt is like what you see, like let me show you this one. This thing, the greater than followed by the space. That's prompt. So let's see. So that's the what you have to initialize the readline with, and then after that, this terminal async is just a thin wrapper on top of the readline object or struct that comes out of this constructor function. So it basically returns a tuple. One is this thing called readline, and another thing is this thing called shared writer. So the shared writer is basically the replacement of standard out. And the difference with this standard out versus a regular standard out is that when multiple tasks use the standard out to dump output to the terminal, it respects the state of readline. So the prompt, this prompt is not going to get clobbered. So you say start task 1, and you say start task 2. You'll notice that the prompt is down here. This is a stateful prompt, and it supports all kinds of things like control left to right. It supports up for auto completion. It supports control D, control E, control all kinds of like shortcuts. And so this is the beautiful thing. I just hit control D to get out of there. So that's what really the purpose of readline is, because we want concurrent access to standard out. So the standard out actually here is a shared writer, and that is essentially something that implements the write trait, which is very similar to what standard out does in the first place. So, and then they kind of work hand in hand. So the way it's architected under the covers is that one readline produces at least one shared writer, and the shared writer means you could just clone it and use it as as often as you need. And under the covers, you can look at the implementation of shared writer and readline, and it'll show you like what a shared writer is. Essentially, there's like one of these multiple producer, single consumer channels. This comes from a different crate than Tokyo. This is actually from the futures channel. So when I originally got this crate, it had dependencies on a lot more. Then Tokyo, there's like async, STD, and so on, and I removed all those dependencies and rewrote a whole bunch of stuff, so it just uses Tokyo. I might do further cleanup actually and remove dependencies on all these other things and just kind of stick with Tokyo, like get rid of futures channel and futures util, because MPSC channel, for example, is available in Tokyo, so we can, that could be. I might actually do an issue, create an issue. So if somebody wants to work on this, it's like some internal refactoring to remove the dependency on this thing, future channel. Okay, so that's a sort of a whirlwind overview of what terminal async is, readline is, and shared writer. So essentially, when you create a new readline, it just splits itself up into a readline and a standard out. This can be cloned incessantly. This, on the other hand, cannot, which is why I wrapped it in an arc mutex. So the arc is actually this from standard library, and mutex is actually from Tokyo. So it's a non-blocking asynchronous mutex, which is pretty cool. Tokyo is pretty efficient, so even though it looks like a lot of stuff is happening, it's actually at runtime really, really efficient, and it's actually very easy on your CPU. Okay, so let's look at the constructor function for terminal async. So this thing really is, we really want people to use terminal async rather than readline and standard out. These are roughly implementation details. And most of the time, readline shouldn't really be exposed. Just standard out needs to be exposed, and even that doesn't need to be exposed. I mean, ideally, we would make these private and just have a function called clone standard out. So let's say if you wanted to get access to the standard out, you would just call clone standard out. Similarly, you should never, well, I should say never, but ideally, or not ideally, most of the time you probably don't even need access to readline. It's there under the hood, let's say. But really what you want is you want to be able to print things to the screen asynchronously or concurrently. And so there's these functions: print output in flush, print raw in flush, print line raw in flush, and so on. And essentially the gist of it is that they just take your output, your content, which just implements display trait, and they just dump it to the standard out. This is the concurrent one, the shared writer, and then they flush. That's literally it. I mean, there's not a whole lot of stuff going on. It's pretty straightforward. So let's clean it up a little. I feel a little bit uncomfortable with the way this implementation is right now. So really, the readline, nobody needs access to this. Let's do the simple one first. So let's see what trouble we run into. I'm sure a bunch of stuff will go red. Nope, nothing went red. That was fantastic. So apparently nobody was accessing this field anyway, which is fantastic. Let's see this one. Is anyone accessing this field? What? Nobody's accessing that field? Okay, great. So all the access was coming through these methods, which is fantastic. Rust is not object-oriented, but there are situations where taking related functions like this and kind of wiring them together makes sense. One thing I did notice is that this code block is just repeated, and might as well just use the flush function. So we can just say flush self. Self. What am I? Sorry. There we go. So this way we just replace this with flush. Oops. Oh, wait. And here we can say self flush. That way, it's a simple little refactor, but we're just essentially using this flush. And flush is pub because there are situations where you might want to flush the output. Okay, so one thing I did notice is when we were running the main function and we went through this client code path, there was actually a bug with the prompt. I noticed that the prompt wasn't being displayed properly, so let's go look at where the prompt is displayed. Don't know why this wasn't flushing. That was weird. Okay. It says printline raw and flush, which basically takes whatever content you give it and uses this shared writer, this asynchronous standard out, and just uses the write line macro to print it and then flushes it. So that should work. So let's run it and see what happens. So let's do the client and see if that does anything. Oh, it would help to have a server. So let's do this. Interesting. I didn't know that. That's weird. Why does it say Python? It's strange. What is going on with this? Okay. Okay. What the heck? tcp-api-server. I think we had the tail going here. Okay. I don't know why there was a Python. That was weird. And then here we can go to tcp-api-server and actually run the server. Let's see. Okay, server's running. So let's run the client. Okay. See, this prompt is missing. It says enter a message, but then the greater than is not being displayed. That's odd, because if I hit any key, it displays the prompt. So that looks like a bug. I wonder what's going on there, because it says, could be because of sleep. Ugh, yeah, that's probably what it is. So cleverly, I thought I would put a sleep in here for random reasons. I'm gonna take that out, and now it should work. Nope, it still doesn't work. It wasn't asleep. Okay. So what is going on here? Do I do another flush? Let's see. That seems redundant because I already called flush. Let's see if that doesn't. Nope, that doesn't do anything. So so at write line. So the backslash n is necessary for this in the implementation details for readline and its standard out. It actually needs backslash n in order for it to actually print things. Like basically, it clears out the buffer and does actually flushes itself. And I think without, let's see, where's flush? I think without the \n, it doesn't actually do anything. It's like a no-op because it's looking for this one. So let's see, why is this not working? So maybe if we do, this is just a hack, but if we put in another read line, I wonder if it'll change anything. No, just puts an enter. Okay, so it seems to be an issue with the prompt. Let's see what's going on here. So we have a whole bunch of stuff being set up, and then we enter the main event loop. There's a delay. That doesn't seem to do anything. Maybe it has some interaction to do with this finish with message. That has a new line. So this is the progress bar. When you spawn a progress bar, in order for it to actually work, it has to dump a unnecessary \n, and then so it basically types, like foo dot and then carriage return line feed, and then in the next iteration it moves the caret back up, clears the line, then types foo dot dot carriage return line feed, and when you run it over and over again, it looks like dot 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 is happening in an animation. So that's how this animation is executed. And then at the very end, when the message is removed, it moves the cursor back up, clears the line, and then prints the finished message with a \n, so the flush will work. So maybe there's something happening in that asynchronous dance, so to speak, that's causing the problem. So let's do this. Let's remove the progress bar altogether and see if that resolves our issue. Oh, what the? That was weird. I see the prompt, and then I see the prompt going away. Okay, this is definitely a bug. Okay, I'm going to investigate this further in a separate stream because, let me write this down. This is definitely a bug. So basically, when running the client, actually, you know what? Why am I writing this on paper? Let us do this the right way. Where's the GitHub? Where is it? It's async. And here we can create a new issue, and the issue is something like in tcp-api-server client, the prompt isn't displayed properly. API server. Disappears, yeah. Really? How do you spell disappears? Sure. Really? Okay. Disappears? Why is this so hard? What? Oh, that was weird. All right, so run TCP blah 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 blah. Okay, so Yeah, something weird. This is not really sure. Okay, so we can submit that as a bug. Okay, so now we have that recorded, which is great. Can sort this out in a separate stream. But yeah, stuff like that happens while you're in the middle of refactoring. Find all kinds of things that weren't working. So let's go back to the refactoring. So, okay, so we have some clarity around sort of like how these the connection points between all these chunks of code are. So we have like readline here. Let's see. So readline. So this is an example that exercises readline. I mean, it's okay in the sense that I was using it to make readline. So it's more like, does it work? Actually, let's see if this works. That is so weird. See, the prompt works here, no problem. Okay, I got it. Hard for me to, yeah, I'll figure out what's going on. There's some strangeness because it works here. But when you run the same thing here, the prompt is gone. But if you, as soon as you type something, the prompt is back. Sometimes it's a sanity check. I'm like, well, is this, actually, let's do this here. Is this VS Code or nope, this is not VS Code. So as you notice, this is the same behavior in a quote-unquote real terminal as it is in VS Code. So this is definitely some strangeness that is going on. Okay. All right. So this terminal async module is, I think, a good starting point because it's already showing us like what needs to be encapsulated. There's a progress bar, which is its own thing. There's the terminal. The terminal really, it looks like, is the main struct that we'll probably be dealing with, along with the progress bar. That's its own struct as well. So terminal is its own thing. Progress bar async is its own thing. And then there's something. So this is really like people should be using this rather than readline directly. And by the way, the reason the readline itself is wrapped in an arc mutex and not terminal async is because now you can just indiscriminately clone terminal async. So if I give you a reference to terminal async, you can just clone it, knowing that there's an arc that wraps it, which is clonable cheaply, and standard out itself is also clonable because basically it's just a one end of a channel, the sender end. So this is totally clonable, hence the clone. So if once somebody has a handle or has a reference to terminal async, they can just clone it around and pass it between threads and tasks, which is pretty awesome. Because the channel also is thread safe, so this is pretty epic. If it would work, it would be even more epic. I mean, you know, in that use case that where it's not working. I mean, it is working here, but it's not working here. Okay. I mean, partially not working. So let's look at terminal. Okay, so this I've identified. Okay, this is definitely something that is the main thing. So we'll probably put a lot of docs here. So this is, I leave myself these notes 00. Like I have a plugin. Where is it? Is it to do or something? No. To do. I think it's to do. Yeah, it's this one. To do plus. It's really good. Really fantastic plugin. And it allows you to essentially create your own tags. So, like as you can see, I have these things called 00, where they're all rolled up in 00. If I do like to do, I have this also. Shows up here. It's kind of nice. So all the to-dos. And I have a whole host of these others. Like I think I have 01. Yeah. So this kind of like, it's a way for me to annotate my code so that I can keep track of like, okay, where was I? Because there's so many files, so many things going on. What's the prioritization? What should I look at first? What should I look at next? So here, Let's see, this one is probably, let's put it as a separate 0, 1. So we can say something like, and this is arbitrary because there's a whole bunch of 0, 0s there. I'm going to leave them alone, and then I'm just going to call 0. And I think I even have refactor. Yeah, there you go. Refactor is there too. So nope, refactor's not there. Let's see what is there. So I think there is 0, 0 somewhere. Oh, and I have a different plugin which colorizes the 0, 0 colon. So I think that's called. I think that's called to do highlight. Yeah, so it's a separate one. This one is to generate that that sidebar, this thing. That's to do embedded, and the other one that I showed you is this highlighter. So this thing does these highlights these lines. So let us see what is going on here. So there should be another place where there's to do plus. There we go. Bookem, bug, done, debug. Oh, and there's no refactor. Okay, whatever. So maybe I can just use 0, 1 then, as I had originally sort of. Yeah, 0, 1. I might have had refactor at some point. I keep changing these around. So this is this is probably the main entry point for the crate docs. So keep in mind samples. So right now these examples are just all using readline, and there's no tests. So a lot of work needs to be done in this crate. So let's see. So that's terminal async with readline and shared writer, and then this part looks okay. That's not bad. So we're kind of like, I'm just kind of like going over at a top level, like what all the structs are, and to kind of get a sense of like what the shape of the external interface for this API is going to look like, because we can easily split this crate up into the external API surface that somebody who's consuming the crate will see, and then the maintainer will see a different surface. And like this is the maintainer surface. We don't need the folks using this crate to be concerned with the, actually wrong file, to be concerned with this these files. These are implementation details. So that's more like how it's put together, and this is more like how someone can expect to use it. So that might be a really cool takeaway from this, is that when you're designing accessible crates or accessible APIs, to think about two parts. One is the how I, the maintainer, am going to implement it. That's my maintainer hat. And someone else using the API, how are they going to consume or access it? And they're not the same. If I take my implementation details and put it in this API surface, it would make for an ergonomic API. So we really want to have a separation of concerns between the two, even though, this is just basically a wrapper, which is fine. We don't want to expose too many details in the wrapper. Okay, so this is going to end up becoming the wrapper, and this is going to end up becoming the implementation, which also gives me a signal that there needs to be a module here. This is in the crate, because I'm going to be moving this terminal async module into here. So this will probably become the underlying implementation module. And this will be the public API module. Okay, so that's more hints. Okay, so we got progress bar. So progress bar is pretty straightforward, self-contained. Terminal, yeah, this is going to be, and also this is also the main entry point, sort of. Progress bar is an adjunct, and I'm not going to say this is the main entry point, because if you're not using a terminal async, you don't really have any need for progress bar async. So because progress bar async has an intrinsic dependency on terminal async. So this needs terminal async instance to work, so this is not the main entry point. Exactly, and so this will also probably need to be moved. I need to figure out how to do that separation between the public API and the implementation modules. So that could be an exercise we look at later. So I'm kind of like staging, thinking about all the work that needs to be done out loud before we actually do it. So probably the next stream is when we're going to be implementing this. This is more like, okay, do a survey to see kind of like what needs to be done and where it needs to happen before actually doing it. So we kind of went through terminal async. This is going to be the main entry point. This is going to be tricky. So this is tracing setup. And tracing setup is essentially, there is a variant of this in here, just in the examples. This was like again, a little hint to me that if I'm writing an example and I need to have a function to initialize tracing, that needs to be part of this API. Otherwise, it's, again, not really ergonomic. You don't need this here to implement the API, but you need this for somebody to consider the needs of somebody using this API. If they use Tokyo tracing, then you need to have this file here, which is like, this is, again, this tells me this is part of the public API service, not the private API service. Also, this is just inadequate because I just did this for this one example just to get this to function. But the quote-unquote real implementation is much more complex. And the real implementation, unsurprisingly, happened when I went to use Rusty Line Async, which is this one. They're called the same because I was like, oh, interesting. Because this is the simplistic version and this is the quote-unquote real version. So this real version has to be moved into this crate, which we will do. So this is another, and this is a bit of it's actually not that big of a job because it's pretty much self-contained. It's just the concepts are a bit not so straightforward because in order to configure tracing, in order to set up tracing and configure tracing, you need to consider this. I'll show you. So if you go to configure tracing, there's these things: none, standard out, file, standard out, and file. And the default is standard out and file. So this is what the user, the end user running this binary is gonna tell the binary using clap. It's gonna configure it to have a certain behavior for tracing. It needs to be extensible. So the clap stuff really is, I'm gonna disconnect it from, so if you look at the clap stuff, the clap stuff is clap stuff. So I'm gonna leave it where it's at. But this setup tracing thing, that needs to be made mostly generic and moved into this Rusty Line Async crate. And the main way in which you use this is you say init. It's just literally just like the one function. It's a lot of work for one function. So the way it works is you say tracing setup init, and then you have to give it a config. And this config is where I gathered all the behaviors that you would like to see. So because in tracing, you can trace to standard out, you can trace to none, basically turn it off. You can also trace to file, you can trace to standard out and file. You can trace to standard out, which is the STD, the standard library, standard out, or you can do the async standard out, which is a shared writer that comes from Rusty Line Async. It's a complicated tree. So this tracing config struct, I made this to contain what I just said, but using the Rust's type system. So essentially, I defined this enum, which describes the different types of, I call them tracing writers. So there's tracing writers. I don't call them this. Tokyo Tracing calls them this. There's a log appender, which basically writes tracing output to files, appends them to a log and rotates them on a schedule. You can also do standard out. There's also ways to configure the tracing itself. There's all kinds of configuration. So just to encapsulate the writer part, we're like, okay, you wanna generate tracing output to standard out, you want to log it to file, or you just want to disable it altogether. That's this none. And for it to work with clap, I implemented the from string trait so that you can go fluidly back and forth between clap and this enum. And it's only a one direction. You only ever need to take the string that you type in from the terminal and figure out what writer it corresponds to. That's what this is. So that's just this one line, and you can have a bunch of them. So, because you can have like, and I'll explain why there's a bunch of them later in the implementation, but because that's how you do standard out and file. Because there's no, because you see there's standard out, there's file, but there isn't like standard out and file. There's no need for this because we have a vec of writers. Tracing level is how many levels you have, like debug, info, trace, and it's just basically saying, okay, I want the max tracing to be the highest granularity to be whatever. So you can say debug or trace or info, whatever you choose. This is for only for the log file and path, and honestly, this should, I made it a string, but it should really be, because it's optional, right? Because if you don't have a writer, which is a file, then you don't need one of these. So what I might do is, as part of the refactor, we might end up with something like this, or path buff, whatever, right? That might be more appropriate. So maybe I'll make a little note here. Probably part of writer file and then something. So we can say like path buff or string, because this has no business here, because if I don't even specify a file writer, why am I having to explicitly specify the log file path and prefix? So, and then finally, this is a standard override. This is a clever way of saying, am I async or not? So if you look at where this is used, you'll see here when the client, so on the client code path, right? When the subcommand is client, when you say tcp-api-server space client, it'll make an async terminal, and then it'll get the standard out from that async terminal and pass it in to standard out override. In the case of the server, which is uninteractive, it doesn't need that. So it just says, I have a standard out override of none. Just use the actual standard out. So that's what this is. This is really nice. This way you can clearly see what's going on. But this is not so nice because I would like to do something similar to this. But to here, that's why I want to move this into probably the writer file enum variant. Okay. So that's just tracing config. And this is just a default. If you don't want to specify this manually, just say new and pass a standard out. And it kind of does defaults for things. We might actually revisit this later, say, is this really needed? I'm not sure. Okay, so writer config. Okay, so this is a bit different. There's something called writers, as you saw, which didn't have standard out and file. And here you'll see writer config. So this is essentially in Rust, a lot of things happen where you take one type, you take an argument, and then you generate a different type. And then you just kind of repeat that over and over and over again. So this is an example of that pipeline where I take a vec of writers and I convert it into a write config. And the write config is the one singular enum that I will then use in order to initialize tracing. So you'll see this all over the place in Rust, and you'll see it all over the place in Rebel codebase, where it's a type plus something, and it generates another type, and then you just keep going. So, so this is so that I can have a match statement, and I can just say, take a vec of writers, which you get from clap, convert the strings into writers, then convert the vec of writers into this writer config, match on that writer config, and actually do the work, which is pretty awesome. So very clever. So there's a bunch of builder. Basically, this is how you configure Tokyo tracing. There's like a bunch of stuff, regardless of whether you say to use the standard out writer or the file writer, whether it's async standard out or sync standard out, doesn't matter. This is the same. Where the paths diverge is here. Oops, that's not right. So that's this one. This is just file writer, and this is... Okay. So it kind of is a bit almost, it's self-explanatory. So here we have like, we convert the backup writers, basically take the array of strings we get from clap, turn it into array of writers, convert the array of writers to a single writer config. And if it's none, we exit, we early return, which is why this is unreachable. And then if it's standard out in file, we do something. If it's file, we do something else. If it's just standard out, we do something else. So that's essentially what, without going into the specifics of what actually happens from purposes of refactoring, this is what init does. So there you go. That's a last file in that module that needs to be refactored. So in the next session, because it's almost an hour, what we're going to do is actually do the work. So in the first video, it's like, well, what is this? Why is it? Why does it exist? Where does it fit? What are the use cases? In this session, this video, we were like, okay, public API, private API. How do you structure these things? How do you even figure out your requirements for good API design? Well, you probably need a consumer for that API, so you can figure out what the needs of most applications or most relevant applications might be from the API, and then there's needs that the API itself has. So we kind of tier that into, we scope it into two separate buckets, if you will. One is the implementation details, the other one is a public API surface. And then it's a journey to figure out what goes where. So in the next video, what we're going to do is continue from this point on and actually do the work. We're going to take this particular module and we're going to put it in the correct crate, and then this code will get way simpler. And then another bug that we found, this needs to be addressed as well, but that'll be a different video, because it happens when you go to refactor, you're going to find things. And on that note, thank you for watching, and see you on the next one. Bye.